Hello everyone. We are still talking about graph algorithms, and in this video we are going to solve minimum spanning tree problem. Assume we have a connected undirected graph G. So we define a spanning tree for G to be a set of edges that covers all the nodes in the graph, and it creates a tree. It means that it is connected, and there is no loop in this set of edges that you choose. So you can see that a spanning tree is going to be, a way to connect all the graphs, but with minimum number of edges. We can have, based on what is the shape of the original graph, you can have different spanning trees. For example, in this graph here, on top, we can see that I'm actually showing two different spanning trees. Okay, finding a spanning tree on its own in an unweighted graph is not a hard problem. You can easily find, use a BFS or DFS, you can create a spanning tree right over the graph. But the problem here is that we are looking for the spanning tree over a graph that actually has some weights associated to each edge, and we wanted to find a spanning tree with minimum weight. The summation of the weights is going to be minimized. So you can also think about this problem as the cheapest way to connect all the nodes in the graph. For example, there is going to be a network of cities. You wanted to find the cheapest way to keep all these cities connected, just maintain those routes, something like that. So in this problem that we have here in the graph, you can see that I have defined some weights associated to each edge, and a minimum spanning tree for this graph can be a tree like this. So if you add the weight of all the edges and check with other possible spanning trees that you can define, you can see that this is going to be the minimum spanning tree for this graph. So the thing is, the problem doesn't have a unique solution necessarily. Depending on the graph, you might have more than one minimum spanning tree possible defined over the graph. But we don't care. As long as you find just one spanning tree with minimum weights, that's enough. It doesn't mean that you have to find all the minimum spanning trees. So if you think about the problem, again, the problem is like an optimization problem, right? You are looking for the minimum spanning tree among all the spanning trees that we can create. So it immediately actually comes to mind that either use the something like dynamic programming approach or a greedy approach. And interestingly, yes, there is plenty of, there is at least three possible greedy strategies which are optimal and helps us to find the minimum spanning tree, the optimum minimum spanning tree. So these greedy strategies, I'm actually writing three of them here, the three main ones discussed in the textbooks. The first one is to start from sort all the edges and always actually just take the edge with the minimum cost if it actually adding this edge doesn't cause creating a cycle. This is clearly a greedy strategy, right? You just actually think about the edges and take the one with the minimum cost, as long as it doesn't create a cycle, because if there is a cycle, it's not going to be a tree, and you don't need that edge definitely. The other greedy strategy is that just start removing completely the reverse of the previous strategy. Remove the expensive edges as long as the graph is still connected. And the third approach is this one. The strategy is completely different than the other ones, but still it is a greedy strategy. It just thinks that this way, that all the nodes should be connected to each other. So start from one node, and for this node, if you wanted to actually keep it connected to the rest, you should choose one of the edges of going out of this node, right? So take the one with the minimum cost and then grow your tree. It's just like you are growing your tree starting from one of the nodes. So I'm going to discuss the first and the third one, which are more famous. So let's see that how the first strategy works over this example. The strategy was to sort the edges based on the cost and always choose the one which is the cheapest one. So if you think about this graph, the cheapest, let me use a different color here. The cheapest edge is going to be this edge 2, right? So you choose this edge, then the next cheapest edge is going to be this edge. The next cheapest edge is going to be the edge, this one. You can see that adding each of these edges doesn't cause any cycles, so it is safe to take them. The next cheapest edge is going to be the one with cost 5. The next cheapest edge is going to be this edge. But as you can see, adding this edge is going to cause a cycle, so I'm not allowed to choose this edge. The next cheapest edge is going to be this one, but still you can see that adding this edge will cause a cycle, so I'm not allowed to add that one. The next cheapest edge is going to be this one, and it doesn't cause any cycle, so I'm going to add it. The next cheapest edge is going to be this one. And again, you can see that adding this edge is going to cause a cycle for me, so I'm not allowed to take it. The next cheapest edge is going to be this one. And basically here we can actually stop. And the reason is that I'm already actually covering all the nodes. So I'm done with creating that spanning tree. Adding any other edge will cause a cycle. So that's it. This is going to be the tree for me. So let me actually just remove, clean and erase these signs. So this is going to be that spanning tree. The cost is minimized and I'm actually covering all the nodes. The steps have been actually showed here through these slides, but I'm just going to skip them. We have seen the result. So this was actually the result of finding the minimum spanning tree over this graph, which was exactly those edges that we took. So this is going to be the full algorithm. This algorithm is known as Kruskal algorithms, named after that scientist who proposed this algorithm. So before talking about the time complexity, just the simple algorithm is that sort the edges based on the weight, the cost of each edge, and then over a loop, I'm going to just check every edge in that sorted order and check as far as I'm not creating a cycle. T is a set of those edges a part of the tree. So as far as adding an edge is not going to cause a cycle, I'm going to just take that edge. Otherwise, skip it. So before discussing about the time complexity here, because this is a greedy algorithm, right, we have to prove the optimality of the greedy choice, and we have to prove that this algorithm really finds the minimum spanning tree. Similar to other greedy algorithms that we discussed before, I am going to use the exchange proof, a type of exchange argument here. So the idea is that assume there is another spanning tree with, there is an optimal spanning tree different than the tree that has been found by the Kruskal algorithms. I'm going to show you that that tree can be changed to be exactly like the tree that the Kruskal algorithms found. So the Kruskal algorithm will be the optimal spanning tree, the minimum spanning tree. So just assume that we have actually sorted the edges in this new, this optimal tree T prime, okay? And just compare all the edges in T and T prime. The cost of edges in T, which is the tree found by Kruskal algorithms, and the optimal tree, which we call it T prime, the cost of edges have been sorted in increasing order. Find the first edge, which is different in T and T prime. Let's call it E prime. Okay, so this edge E prime is in the optimal tree, but it is not in the Kruskal, in the tree that has been found by the Kruskal algorithms. Okay, so if you add, let's just call actually that edge E, which is not in T prime. Okay, so there is an edge in the Kruskal algorithms, the edge that the Kruskal algorithm found, but it is not in the optimal tree. So it is the first difference between the tree T and the optimal tree T prime. So by adding the edge E to the optimal tree, you definitely will create a cycle, right? This cycle here. If you think about all the edges in this cycle, find an edge which is not in the tree that the Kruskal algorithms found. Definitely there will be an edge, right? Otherwise, this is not going to be a tree. So that edge E prime, which is in T, so E prime is a part of T, but E prime is not a part of, it is a part of T prime, the optimal tree, but it is not in the tree that have been found by the Kruskal algorithms. So we know a fact about this edge E prime. The cost of this edge E prime definitely is going to be more than the cost of edge E. And the reason that we claim this is that the Kruskal algorithms sorted the edges based on the cost and always choose the one with the minimum cost before creating a cycle. So definitely E prime haven't been chosen by the Kruskal algorithm. Otherwise, the cost of that should be actually smaller than E, right? So the cost will be greater than E. So in this cycle, you can think that in T prime, instead of taking E prime, I can replace it with the edge E and remove this from the T prime. And because the cost of E prime is going to be greater than the cost of E, greater than or equal to the cost of E, by removing E prime from the optimal tree and adding E, you are going to decrease the cost of the spanning tree in the optimal spanning tree, right? So it is contradiction, or either you actually make the optimal tree better and make it more similar to the tree that the Kruskal algorithms found. So this is enough to prove that all those edges which are different in optimal tree and the Kruskal algorithms can be changed to be exactly like the edges in the Kruskal algorithm. And so it proves that the Kruskal algorithm finds an optimal tree. So what is the time complexity here? Clearly I have a sorting cost here, the number of edges, assume it is m, the number of edges. So the cost of sorting here is going to be m log m for sorting m edges. I have a loop here, okay? This loop iterates over the edges, and each time just check that if there is a cycle in the tree or not. There is a trick to implement this part of the algorithm. There is a specific data structure called disjoint sets. You can find the extensive explanation how this data structure works and the proof of the time complexity of different operators over the this data structure. I'm not going to discuss it here. You can find it in chapter 21, and it has been used in chapter 22 and 23 in your textbook CLRS. But the thing is, the idea of this data structure is that it creates a set for every vertices, every node. And then when it adds one edge, for example, if you have, for example, this many edges, each of them is going to have one set. When you are adding an edge, the set of these two edges is going to be marked as one edge. So both of them will be actually in one set. Then you, for example, added these two, the set of these two edges will be just one set. So these two, these two nodes. So these are going to be one set. Let's just call it, for example, A. The other one, the set is called B. When you are adding an edge between any two components, for example, this one, if you are adding this edge, the set of these two will be merged and create one set. So both of them, after adding this edge, will have one set. So in this way, when you are adding an edge, to be able to check if there is a cycle or not, you just need to check that if the set of both nodes, for example, if you are going to add an edge here, the set of these two nodes, both of them are A, so it means that you are going to have a cycle, so it doesn't allow you to add this edge. Okay, so this is the idea of this disjoint set data structure. And what is the cost for checking the cost for checking the sets is O of 1, but the cost for merging, for example, when you have, let me use this color, when you have added this edge, okay, the cost of merging two sets was O of log of n, where n is the number of vertices. Okay, so basically the cost of checking if there is a cycle or not is going to be O of log of n, where n is the number of vertices, or the number of maximum number of components, the maximum number of nodes that you have in each set. So in total, the time complexity of this part is going to be O of n log n. So the reason is that you would add exactly n edges. So the total time complexity will be the time complexity of the sorting here, the time complexity of checking the cycles and adding edges. So the summation of these two, you can see that this one is larger because m is, out of the log here. You can also write it as O of m plus log n, O of m log n, and the reason is that m can be actually the maximum size of n is going to be n power 2. So because this part can be written as n power 2 and this is inside the log, the 2 in the power can be taken out and you can write it as m log n, where n is the number of vertices, m is the number of edges. There is no difference. Either of them can be written and both are acceptable. Both basically shows the same time complexity. So the next greedy strategy algorithm that I'm going to discuss here is the last one. Actually, this one here, this is very similar to the Kruskal, just the idea and the strategy is completely reversed. You remove the, you think about it in this way that I don't like the expensive edges. So I started removing all the expensive edges unless it is an edge which is really required. It means that if you are making the graph disconnected, you can't remove that edge. So the strategy and the idea is completely reverse of the Kruskal algorithm. So I'm going to skip that one here and explain the last one. That the idea is kind of different. This is still a greedy algorithm, but the strategy and the idea here is that you have to cover all the nodes, right? So it starts from one node and just started growing the tree from one node. It doesn't matter which node you choose, just take one node and grow the tree. So you always wanted and interested in the cheapest edges, so you grow it that way. Let me show you how this one works. I have a full example here. I'm going to choose another node except the one that we have in the next slide. So it doesn't matter from which node you start because you are going to cover all of them. So this time let's just assume that I'm going to start from this node, for example. Okay, you just start from a random node and grow the tree. How to grow the tree? You would definitely wanted to take the edge with the minimum cost, right? So you think about all the edges attaching to this node. The cheapest one is going to be this one. So you would add this edge. By adding this edge, you are also adding this node to the tree, right? So now your tree has 2 nodes and 1 edge. So at this point, you have to grow the tree. By growing the tree, you wanted to add 1 more node and 1 edge. So which edge you have to choose? You are going to grow this. So basically, there are a couple of candidates, right? You can grow here. You can grow here. So all the edges connected to the 2 nodes that you already have can be actually a valid next edge to be taken. So all these edges can be added. But which one you are going to take? The one that has the minimum cost and it doesn't going to create a cycle for you. So among all of these, you will see that the minimum one is going to be this one. So you would take this edge and you would add this node. By adding this node, you are also going to add a couple of other candidates and options to grow the tree. So this edge will be also added to the options and this edge will also going to be added to the options. Among all these candidates, which one you are going to take? The minimum one, right? The one with the minimum cost, which is going to be this one, without creating a cycle. So this node will be added, this edge and this node will be added to the tree. By adding this node, you can't really add any other option to the possible edges. There is no edge that hasn't been added before to the set of possible edges. So you look at all the edges that you have and you take the one with the minimum cost. So the one with minimum cost now is 8, but this is not an eligible option, right? Because it will cause a cycle. It's not going to add a new node for me. It will just add some of the nodes that have been already added. So this is going to be rejected. The next, so by rejecting it, let me actually just clean here as well. The next minimum cost edge that you have here is going to be this one. But still, this one is not a valid option because it's not going to add any new node that we haven't seen before. So this one will be rejected as well. The next edge with the minimum cost is going to be this one, which is going to be a valid edge because it's going to add a new node, right? By adding this new node, I am going to add some options to the possible edges that can be added in the next case, in the next step. So now you have a look at all the possible edges that can be added going out of this part of the tree, and the minimum one is going to be this one, and you can safely take it because it's going to add a new node, so it definitely doesn't cause a cycle for me, right? By adding this edge, you would add this node, okay, and by adding this node you would add some other option as well, like this option. Okay, then you would think about all the edges going out and take the one with the minimum cost. The minimum cost here is this one, but we can't take it because it's not going to add a new node for me. It causes a cycle, so I have to reject this edge. The next minimum edge is going to be this one, and I can take it because it's going to add a new node to the tree. And now we can stop because we already actually covered all the nodes. So the red edges are showing the minimum spanning tree using this new algorithm, which is called Prim algorithm. Here you can see that I've shown different steps of the algorithm starting from a different node. Here we started from this node in this example, and again it's just actually growing, trying to cover all the nodes. So this is the full algorithm. Again, I have created a set of edges for the tree which is empty at the beginning. We also created a set of the nodes that have been covered so far. You randomly choose a node, let's just call it S. It doesn't matter which node. Again, I'm emphasizing that in Prim algorithm, it doesn't matter which node you start from because at the end you have to cover all the nodes anyways. So until you haven't covered all the nodes, C is not equal to the full set of V. We find the minimum weight edge such that one side of the one node from the this edge, one side of the nodes is a part of C, so it means that it has been visited before, and the other part is not a part of C. It means that it's not going to create a cycle. So you add V and you add that E to T. So what is the cost? You can see that I don't have any sorting here, but this part is always finding the minimum weight among a set of actually options that we have. So how to implement this algorithm? The best data structure to implement this algorithm with the minimum cost is using a priority queue. Basically, you need to create a priority queue, and after adding each node, all the outgoing edges will be added all the outgoing edges will be added to that priority queue, and the priority queue always guaranteed to gives you the minimum cost edge, right? A minimum priority queue, like a minimum binary heap, always actually gives you the minimum edge, right? So what is the cost of what is the time complexity of removing something from the priority queue or adding something to the priority queue? The cost will be log of n, where n is the maximum number of edges. So here the cost of adding, pushing any edge to the queue is log of m. Removing or popping something from the queue is going to be log of m. And in total, you are going to have m number of edges. Each one can be added to the queue at most once, removing from the queue at most once. So in total, the time complexity of the full loop here is going to be O of m log m, where m is the number of edges. You have m edges, at most m number of pushes and pops. So the total time complexity of the Prim algorithm is exactly the same as the total time complexity of the Kruskal algorithms. Both of them are optimal, both of them finds the minimum spanning tree for you, and the cost of both of them are the same. And interestingly, both of them are greedy. About the proof of this algorithm, the proof is very similar to the proof that we discussed for the Kruskal algorithms. You can use the exchange argument and show that the tree that is found by the Prim algorithm is the optimal tree. You can just, if it is different than the optimal tree, you just try to change the optimal tree and reach to the Prim algorithm. I'm going to keep it as an exercise for you, but the proof is very similar to what we discussed for the Kruskal algorithms. And here is a link that actually visualized both the Kruskal and Prim algorithms to find the minimum spanning tree. You can try it. It's been implemented to just visualize how the algorithms works. You can create a tree and try either of algorithms and see that how it works. It's just fun to play with it. So it covers the chapter 23 from the CLRS, and it covers sections 1 from chapter 5 of DPV.